Welcome back, everyone, to the deep dive. We're diving into some pretty cool research this time
Oh, yeah.
about retinal blood flow.
It's fascinating stuff.
It is, and we've got a paper here from the IE Biomedical Engineering International Conference,
Okay.
and the researchers are using this technique called Doppler holography. Have you
Yep.
heard of this?
Yeah, Doppler holography. It's really exciting. You can visualize blood flow in the retina with just incredible detail.
Yeah, and they're capturing images at 33,000 frames per second.
Yeah, that's a game changer. It's like going from standard definition to 8K overnight.
Yeah, that's a great analogy. It's mind-blowing. But I think before we get too far into the technology,
Yeah.
let's step back for a second. I think it's important to remind ourselves as ophthalmologists why understanding retinal blood flow is so crucial.
Oh, absolutely. The retina, as we know, is such a complex and delicate structure, and it needs
It needs a constant supply of blood.
constant supply of blood to work properly. And any changes in that blood flow could be a sign of a lot of different things.
Yeah.
Like diabetic retinopathy, glaucoma, even systemic conditions like hypertension.
Exactly. And that's why we're always looking for better ways to measure and visualize that blood flow, right?
Absolutely.
But we all know there are limitations with the existing methods.
Right. Each technique has its pros and cons.
So let's talk about some of those.
Mm.
Fluorescein angiography. I mean, it's been the gold standard for years.
Yeah, it gives us these beautiful images of the retinal vasculature, but it's invasive. It carries risks.
Yeah.
It doesn't give us much information on the dynamic changes in the blood flow.
And then there's OCTA.
Right, UCTA.
Yeah.
They come in very popular.
Yeah, it's non-invasive, great resolution,
Mm-hmm.
but it's mainly focused on the capillaries.
Yeah. And it uses those surrogate markers for flow, not direct measurement.
And then we have laser Doppler flowmetry, LDF.
It's been around for a while. It can measure blood flow,
Hmm.
but the spatial resolution is not great. It's hard to differentiate between the specific retinal layers or to really pinpoint those tiny vascular structures.
It's like we're always trying to get a clearer picture, but it's like each technique gives us a piece of the puzzle, but not the whole thing.
It is. It's like we're getting closer each time, but never quite there.
Right. And then there's LSCI, which is good for visualizing relative flow, but susceptible to motion artifacts.
Yeah,
And then there's ultrasound Doppler, which just doesn't have the resolution we need for retinal imaging.
right. You need that fine detail.
Exactly. And that brings us back to Doppler holography.
Yeah, Doppler holography has the potential to bridge those gaps,
Yeah.
give us a more complete view of those retinal blood flow dynamics, and it's non-invasive
Yeah.
and incredibly detailed.
That's what really stood out to me in this paper. But I have to say, when I first saw the term Doppler holography, my mind was a little bit blown.
Yeah.
So break it down for us. How does this even work?
So it's basically a combination of two things, holography and the Doppler effect.
Okay.
Now, you know the Doppler effect. Think about like an ambulance siren
Yeah.
as it gets closer, and then further away, the pitch changes,
Yeah.
right?
Right.
Same principle here, but we're using light waves instead of sound waves.
Interesting.
So you're using the Doppler effect to actually detect the movement of blood cells in the retina. The frequency of the light reflected off of those moving cells shifts just a tiny bit. And by analyzing these shifts, we can determine the speed and direction of the blood flow.
So it's like we're measuring the echoes of light to map the blood flow.
Exactly, and that's where holography comes in. Think of it like a way to capture three-dimensional information using lasers. They shine a near-infrared laser beam into the eye, and the light that's scattered back from the retina creates a kind of interference pattern. And this high-speed camera records this pattern, and then by analyzing these subtle shifts in those light waves, they can create really detailed 3D maps of blood flow.
Wow. So we're essentially taking a high-definition 3D movie of the blood flowing through these tiny retinal vessels.
That's a great way to put it. It really is.
That's incredible. But one thing I noticed in the paper was that Doppler holography, it doesn't have depth sectioning, which we rely on in so many other imaging techniques.
It's true.
So how does that impact the imaging here?
That's a good question. And it's one of the unique challenges with Doppler holography. You see, most imaging techniques, they allow us to isolate specific layers of the retina,
Right.
but Doppler holography, it sees everything along the laser beam's path.
Oh, okay.
So it's kind of like looking through a window that shows you everything inside a room rather than just focusing on a specific object.
So it's a wider view,
It is a wider view.
but it also makes it harder to isolate the retinal blood flow from everything else in the eye.
Exactly. And that's where these researchers, they had to get really creative with their analysis. They developed a whole new approach to look at the data from Doppler holography and to try and accurately estimate that total retinal blood flow.
Okay, now this is where it gets really interesting.
It does.
So walk us through it. What are the key steps involved in their analysis method?
Sure. So there are two main parts to their method. First, they really focus on those primary retinal arteries that are lying kind of flat in the retinal tissue.
Okay.
And they measure what's called Doppler broadening in these arteries, and they compare that to the surrounding tissue.
Wait, hold on. Back up for a second. What is Doppler broadening?
Sure. So remember, we're using the Doppler effect to detect those moving blood cells.
Yeah.
When light bounces off of those cells, its frequency changes a little bit. Doppler broadening basically means that the range of frequencies in that reflected light gets wider because of all these shifts. And the faster the blood flow, the greater the broadening.
Okay, that makes sense. So by measuring the Doppler broadening, they can get a sense of how fast the blood is moving through those arteries. So what's the second part?
The second part is they apply what's called a forward scattering model.
Okay.
And this takes into account the fact that there's a secondary light source coming from the sclera, the white part of the eye.
Okay.
And this light, it scatters through the choroid and those deeper retinal layers, and they have to include that in their calculations.
So it sounds like they're building this complex model to account for all these different ways light is interacting with the eye.
They are. It's very complex. And this model allows them to calculate the blood flow velocity in the retinal arteries based on that Doppler broadening we talked about.
I see.
And the amazing part is that the only other information they need for this calculation is the wavelength of the laser light and the numerical aperture of the eye.
So just a few key variables for a very complex calculation.
It is. And then to get the blood volume rate, they take the average velocity in each section of the artery, they multiply it by the cross-sectional area of that section, and that gives them the blood volume rate.
Okay, so the pieces are starting to come together now.
Yeah, it's all about putting the pieces together.
I'm curious about the actual experiment. How did they set things up to gather all this data? What did that look like?
So they used what's called a Muckett-Zehnder interferometer.
Okay.
It might sound a little intimidating,
A little bit.
but the concept is actually pretty simple. You're splitting a beam of light
Okay.
down two paths. Okay.
And then bringing them back together. And the way those light waves interact when they recombine, it tells you something about what they encountered along those separate paths.
So one beam is interacting with the retina and the other one is like a reference.
Exactly. Precisely.
Yeah.
And they use a near-infrared laser for this,
Okay.
which is a good choice because it can penetrate the eye without being absorbed by the pigments in the retina.
Smart.
Yeah. And they use these special fibers to split the laser beam, making sure that the light waves maintain a very specific orientation, which is really important for creating that clear interference pattern.
So they're being very precise with how they're manipulating the light?
They are. And then they even diffuse this illumination beam, kind of spreading it out, almost like turning a spotlight into a floodlight.
Okay.
So they can illuminate a wider area of the retina.
Makes sense. They need to see the bigger picture.
They do.
Right.
And then they use a combination of lenses to focus that diffused beam right onto the retina.
Okay.
It's all about precision optics here.
And then on the other side, they have that high-speed camera we talked about,
Right.
capturing that interference pattern as it forms.
Working overtime.
Oh, it's the data deluge.
33,000 frames per second.
It is. It's amazing how far we've come, though. We have the computing power to handle all of this now.
It's true.
It's really impressive. And they use a combination of specialized hardware and software
Yeah.
to manage all of that data.
So it's like having a high-speed film editor working in the background.
It is. It is.
Yeah.
Organizing it, making sense of it all.
Yeah. I also thought it was really interesting that they made their software open source.
Yeah, I thought that was great.
What are your thoughts on that?
I think it's a fantastic move
Yeah.
because it really encourages collaboration
Yeah.
and it speeds up discovery.
Absolutely.
Other researchers, they can just access the code, they can examine it, tweak it, build upon it.
It removes those barriers to entry?
It does, and it allows more minds to contribute to moving the field of Doppler holography forward.
It's like they're saying, here's what we've learned. Let's work together to see how far we can take this.
Exactly. This kind of open science approach is fantastic.
Yeah.
It fosters a sense of community, and ultimately it benefits everyone.
Absolutely. Okay, so we've covered the technology. Now let's talk about the actual analysis.
Okay.
How did they analyze these complex images? And I'm particularly interested in the segmentation process. They went through a lot of effort to isolate those retinal arteries. What
Yeah.
were some of the key steps there?
Yeah, it's a very detailed process
Yeah.
because they're not just looking at a simple picture. They're dealing with an image that includes retinal vessels, choroidal vessels, all sorts of other structures. It's like trying to pick out individual threads in a tapestry.
Right. It's a really complex image.
It is. So first, they need to clean up the image.
Okay.
They apply something called a flat field correction to account for any unevenness in the illumination. Almost like adjusting the brightness and contrast on a photo to make sure everything is evenly lit and visible.
So setting a level playing field.
Exactly. Then they bring in what's called the Frangi vessel segmentation. This algorithm is designed to really pick out those elongated tubular structures in the image, the blood vessels, and ignore everything else.
So the computer is essentially learning to see the blood vessels better than we can.
It is. And this gives them kind of a preliminary map of all the vessels in the eye.
Okay.
But remember, this map includes both retinal and choroidal vessels.
Right.
So they need to refine it further.
So how do they do that?
That's where the temporal correlation analysis comes in.
Okay.
So remember, arterial blood flow, it has that pulse.
Right.
It ebbs and flows with every beat of the heart. This analysis looks for those rhythmic changes in the Doppler broadening.
So they're listening for the heartbeat, but through the eyes.
That's a great way to put it.
That's amazing.
It is. And then they combine this temporal information with that Frangi vessel map to create an even more precise mask that highlights specifically those retinal arteries.
Wow, they're really layering these analysis techniques on top of each other.
They are. It's a very sophisticated process.
Like a detective piecing together all the clues.
It is. But they don't stop there.
Oh, there's more.
There's more. They apply additional filters and thresholds to really fine-tune that segmentation.
All right.
Removing any stray pixels, bridging any gaps in the arteries, eliminating any choroidal vessels that are far from the optic nerve.
So they're really honing in on that network of retinal arteries.
Exactly.
It sounds like a lot of work goes into preparing that data before they can even analyze the results.
It does. It really shows their commitment to accuracy. And it gives us a lot of confidence in their findings.
Yeah, absolutely. I want to acknowledge that this is pretty technical.
It is.
But I think for our fellow ophthalmologists out there, it's important to understand just how much rigor and precision goes into this type of research.
I agree. It's not just about the results.
Yeah.
It's about understanding the methodology, the whole journey of discovery.
It's about appreciating the process.
It is. And I think that's what makes this podcast so valuable.
Yeah.
We're bridging the gap between cutting-edge research and clinical practice.
We're helping our colleagues stay informed
We are.
and understand how these advances might impact patient care in the future.
Absolutely.
Okay, so now that we've laid that foundation, let's get to the results. What did they find?
So they found that the blood flow velocity in those retinal arteries, it's not constant.
Okay.
It fluctuates with each heartbeat.
That makes sense given what we know about how blood flows.
It does.
That pulsatile nature.
Exactly.
Yeah.
And they could really see these fluctuations in detail thanks to that high frame rate.
33,000 frames per second.
It's like watching a high-speed replay of the blood flow in action.
Wow.
They also found that the velocity profile, how the speed varies across the width of the artery, that also changes throughout the cardiac cycle.
Oh, interesting. So it's not just how fast the blood is moving, but how that flow pattern changes within the artery itself.
Exactly, you got it. During diastole, when the heart is relaxed,
Right.
they found that the velocity profile was more parabolic.
Okay.
Fastest flow in the center of the artery, slower flow near the walls, which makes sense.
Right. It's like a river. The current strongest in the middle.
Exactly. Perfect analogy. But during systole, when the heart contracts and pumps out the blood, they saw that velocity profile flatten out.
Oh, wow.
The difference in flow speed between the center and the walls, it became less pronounced.
So the pulse of the heartbeat is actually reshaping the blood flow within the artery.
It is. It's really fascinating.
That's incredible. But even with such an amazing technique, I'm sure there are still limitations.
There are.
What were some of the challenges that the researchers highlighted?
So they mentioned that their current setup might be underestimating the total blood volume rate a little bit
Okay.
because of that frame rate limitation.
Even at 33,000 frames per second.
Even at 33,000, they think they might still be missing some of those super fast flow changes
Okay.
that happen right at the peak of systole.
It's like trying to film a hummingbird's wings with a regular camera. You're going to miss some of those movements.
That's a great way to put it. You're absolutely right. So they think Increasing the frame rate even further could improve the accuracy.
Makes sense.
But even with this limitation, their findings are really consistent with other studies that have used different methods.
That's good to hear. It sounds like this technique has a lot of promise.
It does.
What other areas for improvement did they mention?
They talked about the need for more robust automatic segmentation algorithms.
Okay.
Right now, you still need some manual adjustment to isolate those arteries, which can, lead to some variability.
Right.
So developing smarter algorithms that can do this segmentation more accurately and consistently.
That would be a huge step forward.
It would be a huge step forward. It's
Yeah.
like we need to teach the computer to see those arteries as well as we can. And we also need to develop, standardized protocols for interpreting these images.
That's true.
What are the normal ranges? How do those values change in different diseases? We're opening up a whole new world of data here.
We are. This has been a fascinating deep dive into the world of Doppler holography.
It has.
What's the key takeaway you want to leave our listeners with today?
I think the main takeaway is that Doppler holography has the potential to completely change how we diagnose, monitor, and treat retinal vascular disease.
It's really exciting.
It is. It gives us a whole new way to look at and measure blood flow dynamics. And as the technology gets even better,
Yeah.
I think we're going to see even more applications for it, not just in ophthalmology, but maybe in other areas of medicine too.
It's an exciting time to be in this field.
It is.
Thank you so much for joining us on this deep dive.
My pleasure.
We hope you found it informative
I hope so too.
and inspiring. And for our fellow ophthalmologists out there, we encourage you to keep exploring this research. The future of retinal imaging is looking very bright.
It is a